Okay, so we've got a bit of content to get through. Hopefully these content things are relatively small. And after we've done those content things, we can then push into questions that you have in particular about the exam. That said, office hours, the lab, all of those things are times and places where you can definitely get those questions answered. Where we ended last week was looking at the ideal gas law, and a question like this, we could have gone through and really quickly set up in our standard format. Because we're at STP, we can set it up and say, what do I want? Moles. What do I have? 2.34 liters. Since they're not the same things, what do I want? Moles. What do I have? Liters. That is a conversion factor that we're required to memorize. So that's from memory. 22.4 liters was 1 mole, and we now have an answer. Right? That works because we're at STP, and that's phenomenal and great. Okay? If we're not at STP, that system crumbles. Right? And so what we talked about last week was saying that we could still go through and solve this using PivNert, and really that 22.4 liters is equaling to 1 mole comes from PivNert. Right? It's just a simplified calculation from PivNert. Right? Ultimately, you're responsible for the one in red. For PivNert, what you're responsible for is understanding how to interpret it. Right? And that gets into kind of this bottom line. Your responsibility, you need 22.4 liters is equal to 1 mole. Ideally, you also recognize the utility of PivNert. Right? You can either use it or your own talents and relative experiences with gases to evaluate relationships. So for instance, volume and temperature. How are those related? If I increase the volume or increase the temperature, it's a little bit easier to observe. What happens to the volume? Does anybody try to heat up a balloon? Or seen those big fancy balloons flying through the sky? How do they get them to fly through the sky? Heat. They put heat into them, and that causes the balloon to inflate. The volume of the balloon increased. Okay? We can see that from PV equals nRT. If temperature gets bigger and all other things are constant, what has to happen? The volume is also going to have to be bigger so that the equality holds true. Okay? So you can use PivNert to establish those relationships. Pressure and volume, what happens in that case? Okay, they're inversely related. And you might say, well, PivNert doesn't show that. Well, because PivNert doesn't show that because we haven't rearranged it so that we can see that. If the volume gets bigger, the denominator gets bigger, which then means the other side has to get smaller. Okay? So we can see those relationships out of PivNert. They're inversely related. Okay, so PivNert can allow you to establish those relationships, or what you can go through and do is just based off of your own knowledge, you can see those relationships. Okay? Officially, you should be able to quantify them. The quantification is going to come from PivNert. Okay? Or, again, just recognizing those kind of relationships. Okay? After that, we encounter Dalton's law of partial pressures. Because we're looking at ideal gases, all gases have no volume, so I don't care what substance it is. Xenon has the exact same volume as helium. And that sounds really, really weird because when we look at xenon versus helium, what might we say about them based off of the periodic table? They're in the same family. They're not in the same period, though. And when we go down the column, what happens to the size of the atom? The atomic radii gets bigger. And yet when we look at ideal gases, we end up saying that xenon has the exact same size as helium. Right? So when we look at atomic radii, we're now focusing on an individual atom. When we're looking at gases, we're not looking at individual atoms anymore. Okay? We have to change our perspectives on those molecules to fit ideal gas systems. And according to an ideal gas, they have no volume. So size is irrelevant. Right? They don't interact with each other. So Carbon dioxide versus a noble gas, exact same properties. Oxygen versus a noble gas, exact same properties. Okay? We know that to not be true, but when we consider ideal gases, we make it as an ideal situation as possible. Okay? Because we've made those assumptions, this is where Dalton's law of partial pressure comes in. I can add up the pressures of each of the individual gases. All together, that's going to be the total pressure of the system. Okay? Ideal gas law allows me to do that. And that ideal gas law is ultimately Pivner. Okay? So if we looked at an example, if we have a sample of a bunch of noble gases, I could look at the partial pressure for each of those gases. What would the total pressure of the sample be equal to? How do you figure it out? That's it. You literally just add the numbers up and you're done. Okay? That's Dalton's law of partial pressure. Okay? Has a big fancy name, but all it means is you just add up all the pieces and that's the total pressure. That's it. Okay? One of the other kind of big things that comes out of ideal gas law, okay, or Pivner, we're going to set it up this way, okay, is absolute zero. If we think about the temperature, the units on the temperature used in ideal gas is Kelvin, not degrees Celsius or Fahrenheit. Okay? Why not degrees Celsius or Fahrenheit? Both degrees Celsius and Fahrenheit can achieve negative values. If I put a negative temperature in here, what does that mean has to happen over here? I would have to have a negative pressure, a negative volume, or a negative moles. This isn't a change, okay? So you can say, well, one drops. No. This is not a change. This is an absolute. I have negative pressure. Not a change in pressure going down, but a negative pressure. I have less than the existence of a force. Okay? And that, and shaking your head, that can't be true. Exactly! It can't be true. Okay? I can't have a negative pressure, a negative volume, or negative moles. If those can't be negative, what does that mean temperature can't be? Negative. So I can't use degrees Celsius or Fahrenheit. This is why we created a new unit system to measure temperature. And that new unit system says that the absolute lowest we can go is 0. Okay? Because once we've achieved that 0 temperature, the other terms become 0. And I'm allowed to have nothing. I just can't have negative nothing. Okay? Or negative something. That doesn't make sense. Okay? There are all sorts of laws of physics that tie with this that can get it a lot more complicated, but ultimately that's the easiest way to envision this. Okay? What we get out of gases is that we have an absolute temperature. That absolute temperature minimizes at 0. That's why we have kelvins. Kelvins was invented from gas law. Okay? So absolute 0, we can't achieve lower than 0. Right? And for that matter, can we have no particles and measure anything? Well, if there's no particles, how do you measure? You can't. Okay? So we even have a hard time even saying, well, we've got absolute 0. How do you measure something without having something? Right? So that's the big lesson from kind of gases, is that we achieve this 0 value, and that's kelvins. Okay? Now what we've done to do is a big, big jump. It was going to be a big jump regardless, because we've now finished gases, and what we were going to do is shift into limiting reagents and percent yields. And instead what we're going to do is jump into empirical formulas and address what's going on with our formulas first, and then we'll backtrack into percent yields and then limiting reagents, because limiting reagents are the hardest one to deal with. Okay, so empirical formulas. It is the fully reduced whole number ratio. So if I asked you for the formula for sodium chloride, what would you tell me? So sodium being Na and chloride being Cl. So you would tell me NaCl. How many of you would tell me the Na2Cl2? Is that a valid formula for sodium chloride? Okay? You should be saying, no, absolutely not. I'm not allowed to say Na2Cl2. Because when we talk about ionic compounds, the ionic formula must be the fully reduced ratio. Okay? So we've already really addressed that. Isn't that what an empirical formula is? Not really. Okay? An empirical formula is really applying to a covalent compound, not an ionic compound. Ionic compounds are required to be shown in their fully reduced ratio. Okay? Because they're a larger conjugated network of atoms or repeating network of atoms. So it doesn't really make sense to use empirical formulas for ionic compounds, okay? Because they're required to be there. Okay? But what happens if we move to a molecular compound like benzene? You don't need to stress about how I got this structure, but this is the structure for benzene. What is its chemical formula? I know I'm drawing it. What is its chemical formula? Or molecular formula?
So H6C6.
Okay. C6H6 is technically the proper format. We aren't concerned about format, okay, necessarily. So there was the other option of saying H6, C6. Technically, C6H6 is the correct one. Okay, don't stress on that. You won't get tested on it. Okay, is that an empirical formula? No. To be an empirical formula, what would I have to write?
CH.
Just CH. Would that make sense for the compound of benzene? No. Okay, it doesn't match. For an ionic compound, we're allowed to reduce that down because what happens in an ionic compound? Okay, I take sodium chloride and now I just repeat all the way through and everything makes sense. I can piece that together. That structure doesn't translate to covalent compounds. Okay? I'm not just repeating CH. Notice there's double bonds in here. Hydrogen is only bonded to one carbon. Okay? It's not a repeating system. Okay? So the empirical formula removes a lot of information. So the question would become, well, why would we use the empirical formula to represent benzene? We don't. Okay? Where it ultimately comes from is that if I don't know what that compound is, I can go through and run it through a series of tests. Those series of tests will tell me how much carbon and how much hydrogen are present. Okay? And I can determine a ratio between them. That ratio, I don't know if it's CH or C2H2 or C3H3 because I don't know the exact ratio. All I know is that at a minimum it has to have one carbon and one hydrogen. Okay? So the empirical formula is really just an experimental discovery. What we would do is run more experiments to figure out the exact ratio. What was the exact number between them? Okay? So why is this a bit silly? It's kind of an archaic method. It is still used, but we have a lot of other techniques and fancier equipment that can get at more information than just the chemical formula. Okay? So why do we talk about it? I would argue we're going to talk about it because what it does is it really draws attention to what does that formula represent. When we look at the formula, C6H6, what do those numbers mean?
The amount, the total amount of each element atoms that are in there.
The amount of each atom present in that molecule. Can you count atoms?
No.
No. So what else could it represent that would allow us to be able to count? The moles. So really the whole point of empirical formulas is to reinforce the idea of the information stored within a formula. Those can be atoms in a molecule. They could also be the number of moles in 1 mole of the compound. Okay? So it's a unit reinforcement. That's it. Okay? So what are the steps to determining an empirical and molecular formulas? So here they all are. We'll deal with empirical first, and then we'll deal with molecular. Ultimately, you'll be given some information. That information is what we would have found in an experiment. Okay? That information in the experiment is, well, what was the mass of carbon in that sample, or the mass of hydrogen? What was the mass of all of the elements, individual elements within that compound? Okay? So great, I would know the mass of each one. But a chemical formula doesn't tell me mass, it tells me a counting unit. Well, what's the most popular counting unit in chemistry? Moles. So what should you do to the gram amount? Convert it to moles. So if we look at our very first step, convert all of the units that you're given for each element into moles. Okay? The context of how that information is given can be different. Usually it's given in grams if we want to keep it really straightforward. Sometimes it'll be given to us in percent. Okay? Ultimately, both cases, you're just converting into moles. If it's given in percent, just assume a 100-gram sample. Why 100 grams? That equals 100%, which means each of the percentages I'm given can now be converted into or written as grams of that substance. Okay? So if I have a 20% carbon sample, if I say the sample is 100 grams, how much of that sample is now carbon? 20 grams. Now do I have grams? Yep, I can go back to 1a and just convert grams into moles. Okay? The next step, I'm going to divide all of the mole amounts by the smallest mole. Remember, this is to get a whole number ratio. Okay? The number of moles that I calculate may not come out to be the smallest whole number ratio. It may not even be a whole number. Okay? So I divide them all through by the smallest number. That's going to get me to the reduced ratio. Once I have the reduced ratio, it's just a question of dropping the numbers in. All right? So let's take a look. Here's a sample. An unknown compound of radium oxide is found to contain 0.726 moles of radium and 12.3 grams of oxygen. What is the empirical formula? So first step, critical thinking. Is this a proper question for empirical formula? For a hint, I'm going to underline this species. What is radium? It's Ra, yes. And Ra happens to be a metal. What kind of bond do we have in radium oxide? An ionic bond. And we said empirical formulas apply to covalent compounds. It doesn't make sense to really be using an empirical formula for radium oxide because it's an ionic compound. So this is technically a bad question. It still gets at the idea for the basic format, so we can still run with it. Okay? So what we're being asked to discover is if I have radium and I have oxygen, how many moles of radium, how many moles of oxygen? Am I told either of those?
We're told the moles of radium.
I am told that the moles of radium is 0.726. Have you ever seen a formula with decimals in it? Why not? They have to be whole numbers. You're looking at effectively the number of atoms there. I can't have a fractional atom present in that formula. Okay, so we already know that's going to have to get manipulated. Am I given the moles of oxygen? No. What am I given for oxygen? Grams. So what should I do to the oxygen? Convert it to moles. So 12.3 grams of oxygen needs to become moles of oxygen. Where do I find, what do I want? Moles of oxygen. What do I have? Grams of oxygen. Where's that information found? Periodic table. All right. If I had a calculator and run that through a calculator, what do we get? So a good question would be how many sig figs? We should run with at least 3. Okay, when in doubt, keep 3. So 0.76.
8 or 9.
Okay. I now have the moles of oxygen, so I could go through and say, well, it's radium 0.726, oxygen 0.769. Is that a proper formula? No. What was the last step of empirical formulas? Take the smallest mole amount and divide all of your numbers by that. So 0.726 divided by 0.726, 0.769 divided by 0.726. What would we end up with? RA1 and O.
That's a good question.
1.05. We didn't hit an exact whole number. How close is that to an exact whole number? Pretty dang close. In fact, it's so close, it's close enough. And our empirical formula becomes RAO.
So what would happen if we had like, where RA was 1 and O was like 1.5?
Okay? If we came out with our numbers, so when we look at the end, what numbers could we possibly get for those? We can get whole numbers. Those are relatively straightforward. Okay? What if it came out as 1.5?
Just round.
Which way do you round? At 1.5, you're exactly in the middle between both. Where do you round?
You round up
So we could try and do the old rounding thing way back when with dealing with sig figs. Ultimately, that's not going to work out very well here. Okay? We're at a half. We need to get rid of the half. What can you do to get rid of a half?
2, 5. 5, you get a quarter. Multiply by 2.
Multiply by 2. You're like, well, that seems awfully silly. But if we multiplied this one by 2, what do we have to do to the other one? You multiply them both by 2. What happens? Your half value disappears, and you now just have slightly more of the other. Okay? So that half value is tricky to deal with, okay? But that's ultimately all you're going to end up seeing. You'll either hit exact whole numbers or you'll hit an exact half, right? Within an error of estimation, which is roughly 5%. Right? If you're hitting something well outside those ranges, it's probably because you did a math mistake. Okay? Yes?
You said this type of question won't work because it's
It's not so much that it doesn't work, it's that we really shouldn't be doing it.
So on a test, if we get a question like this, will that be a trick question to it's really wrong?
So how else could I have known that the formula was RAO? What is the charge on oxygen? -2. How do we know that? You're supposed to memorize. What's the charge on radium?
+2.
It's a +2. How did you know that?
It's in the second.
It's in the second column. Are you required to then be able to know exactly how much of each of those you should balance? Yeah.
I thought we weren't supposed to memorize the charge on radium.
Where is radium?
Oh, it's in the second column.
It's in the second column. Done. 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 Don't start throwing in weird things. It's in the second column. You should know it's a +2. Right? Second column, you're required to know it's +2. First column, it's +1. That's how it works.
I was only thinking back to the play positive. There's only guys memorize a couple of them.
And if you even go into the play posit, I said group 1, group 2, +1, +2. The slide, because the textbook has decided to go through and label some things and not. If you start using too much of what the textbook images, that's where you'll run into problems. Right? What if we'd had vanadium and oxygen? Do you know the charge on vanadium?
I didn't even know that was an element.
Okay. So no, if you don't know it, we could do this to go through and figure that out. Is it the best usage of it? It works. Okay. Should we be calling it an empirical formula? No, because it's an ionic compound. But does it get me that whole number ratio? Yeah. So the method still works, even if I shouldn't be calling it an empirical formula. Does that make sense?
Yeah.
So let's try one where it's an exact empirical formula. This is a much better sample to test. Okay? We now have carbon and hydrogen. Since both of those are nonmetals, this would be a covalent compound. So this works out perfectly. Okay? I want to know how many carbons to how many hydrogens. So X and Y. Okay? The units for those X and Y, the most useful unit to us is moles. We could do it as atoms, and you're welcome to go through and run that calculation. It's actually a lot more work. Okay? But you are fair to go through and do that. Okay? So how do I convert X? So what did I say X was? What is it trying to find? What is X? The moles of carbon. What information am I given about carbon? I'm told that I have 24.0 grams of carbon. Are grams of carbon the same thing as moles of carbon? No, so what do I need to do? Convert it. Where grams of carbon, what I want to get rid of on the bottom, what do I want? On top, moles of carbon. Where do I find that? The periodic table. The periodic table tells me 12 grams of carbon is 1 mole of carbon. I go through and solve that, what do I get? 1.5. I'm pretty sure that comes out exactly as 2. Okay. What do I do for Y? What was the solve for Y trying to equal? Moles of hydrogen. What was I given about the hydrogen? Grams. Okay. Grams of hydrogen. On the bottom, moles of hydrogen. Where do I find that information? Periodic table. 1.01. I go through and do that math, and I end up with something that's like 1.99. Let's just say it's that. Now what's my next step? Put that in the formula. So I get C2H, 2, right? Because that comes out to be about 2. You're shaking your head no. Why?
You see you have to divide everything by the...
Remember, your empirical formula must be the reduced ratio. Don't get lured in just because those numbers came out close to being whole numbers. You still need to go through and divide them by the smallest of those two. Okay? Divide by 0.99, divide by 0.99, or 1.99. The top one comes out to be, the bottom one comes out to be 1. The top one comes out to be 1.0 something. Let's just say 1.09. I don't really know. So our formula is actually C1H1. Make sense?
Yeah.
So your empirical formula, the whole point of it is recognizing that the numbers as subscripts are moles. Did you already know that? You should have, okay? Because we've used it before. It's now just another way to evaluate that information. That's it. Okay? I would argue it's a bit of a silly thing to do because it's just an extra step of going through and doing this because that technique is kind of archaic. Okay? Still gets used, it's just kind of archaic.
If it's one,
Determining those numbers.
If it's 1 and 1, do you have to list the 1, or can you just write it as?
You don't have to list the ones. You could just write it as CH, yes. Okay? The technique is where did we get the numbers 24 grams and 2 grams? Okay? That's the technique that actually drove why we're talking about empirical formulas. Okay? Which, does the textbook tell you why those numbers are coming about? No, they just say to do it. The technique is the actual experiment that just doesn't get done as often anymore.
So on the exam, because I noticed that with like carbon we use just 12, but hydrogen we actually use the actual value 1.01. On the exam, do you want us to use exact values or like round it the way we did with carbon?
Because I thought carbon just came in at 12. You should use all the sig figs that you have access to. Yeah. And if you go through and adjust it, you're not going to get a different number here.
No, I know.
Yeah, but yes, you should. I understand where your question is. You should use as much information as you have. Yeah. Okay. So that's our empirical formula. How do we get up to a molecular formula? Okay, well, the molecular formula is the exact whole number ratio between those. So if we looked at that same question, there it is. It's our empirical formula. Well, when we solved, wasn't it C2H2? So shouldn't our molecular formula be C2H2? Okay. Well, that's making the assumption that we have exactly those ratios in that compound, or those masses, that it exactly comes out to be that. We don't know how many of those individual molecules are present, so we can't determine that exact ratio. Okay? So all those numbers give us is C1H1. To get the molecular formula, I have to know the next step. Okay? I have to know the molecular mass. Okay? So if we go through and look at this and line this up, our empirical was CH. Our molecular is CXHX. We'll deal with that X in a second. And we know its molar mass is 78 grams per mole. Why did I say CXHX? Why are they both X?
Because we don't know how much of it is composed of.
If I don't know how much of each of those, wouldn't this be CXHY?
No, they're both one.
How? Say that again.
They're both one. So
The molecular formula is coming from the empirical formula. And in our empirical formula, what's the ratio between C and H? 1 to 1, which means when we go through to our molecular formula, they're going to have to be the same. Okay? So if this empirical formula was CH2, what would my molecular formula be?
X and Y.
I could shift to X and Y, right? Because they're now different. I could also shift to CXH2X. Okay? Make sense? So your empirical formula actually tells you what you should be doing with that. Okay? What those should be, X's and Y's or X's and X's. Okay? So how could I possibly figure out what those X's are?
Well, if they're equal, and you have two elements, can you just do 78 grams divided by 2? You have two elements, and if they have to be equal,
Well, what's 78 divided by 2?
39.
Okay? So you're saying our formula should be C39H39?
I would guess so, or I would assume so.
Okay, what is the mass of 1 carbon?
12 point.
What is the mass of 39 carbons?
A lot.
460.
460. So just the mass of carbons in C39H39 is 460. The mass of our actual compound is
78.
78. So no, your method doesn't work. Okay? That does scale, but you're doing the wrong divisions. We've got to decide how we scale up. What are we comparing to do that scale up?
The moles.
Okay? Does this 78 tied to moles?
No, that's how much the gram.
It's tied to grams. So what we're scaling up is not the moles necessarily, but
Grams.
the mass. Okay? What is the mass of CH? 12 plus 1.
13.02.
Okay? 13.02. I can accept that. Say that again.
It's not 78, so
It's not 78. So it can't possibly be CH. That's not my molecular formula because the masses don't match.
you just keep going up until you get.
Okay? So one option is to say, well, it's C2H2. What's the mass? Carbon weighs 12.
26.04.
26.04. Did that work? No. So scale up. C3H3. What's the mass?
39.06.
39.06. C4H4.
52.08.
Still not right. C5H5. God, I hope there's a better way to do this. I wonder if, we had it on that previous slide where I said, this is what you should do. Don't worry, it went really fast. Oh, wait, I did. What did I say to do? Kind of along the lines of what James had suggested. I take the molecular mass, that's 78, And I don't want to divide by the number of atoms because it's the mass that's important. What do I want to divide by? The molar mass for the empirical formula of 13. What number do I get? 6. What this is saying is that 6 CHs fit into the molecular compound. Which means what should my molecular formula be? C6H6. What is that total to be? 6 carbons would be 72 plus the 6 hydrogens? 78. Damn, that matches. There it is. Okay. So all we're looking at with that molecular formula is how many times does the empirical formula fit within the molecular formula. That fitting is just doing that division. That gets us that 6. Okay. As Ali suggested, you could just start scaling up the numbers and seeing what happens. It works. It absolutely does. And as long as that scale up is a relatively small scale up, it's not a big deal. But if we scale it up by 100, that method's going to suck. Okay? So we want to be able to address how do we scale up, okay, without having to do multiple trials. That's the whole point of division. How many times does it fit inside? Okay? Kind of makes sense? Okay. Interestingly enough, what was C6H6?
Benzene.
That was benzene that we had just talked about. Okay? So, we break it down. Determine the molar mass of the empirical formula. In our previous calculation, what was it? It was 13. Divide the molecular molar mass by the empirical molar mass. So 78 divided by 13. Multiply the empirical whole numbers, so in our previous case, C1H1, by the number from calculation 2. What was our number from calculation 2? 6. 1 times 6, 6. 1 times 6, 6. And that's how we got our formula. Make sense? So when it comes to empirical and molecular formulas, I would argue it just makes sense to memorize this process and just be done with them. Okay? Just get them out of the way so you're finalized and moved on. It is ultimately following the exact same patterns that we've been following the whole semester. It's just a small extra step and recognizing that that's what you've done. Okay? I don't think it's worth the added value to spend the time to kind of process that. I think it just makes sense just to do it. Make sense? Ish? Ish. Limiting reactant concept. Okay, so we're going to look at this one kind of quickly. Grilled cheese sandwiches. Okay, you need 1 slice of cheese, 2 slices of bread, and you make 1 sandwich. So there we go, right? There's our recipe. 1 cheese, 2 bread, 1 sandwich. You have 5 slices of cheese, 8 slices of bread. How many sandwiches did you make?
4.
You did that awfully fast. How'd you do that?
Because it takes 2 slices of bread and you get 4, and then you have an extra cheese left over to try.
Okay, so what you just did in your head is exactly what I want you to do on paper with a chemical equation. You said I had 8 slices of bread. I don't feel like writing out all of bread, so I'll just do BR or BD because I'm already there. And I want to turn that into sandwiches. SW for sandwiches. 2 slices of bread made 1 sandwich. And you got 4. But you didn't stop there. Because you actually added the next statement. You also said 5 slices of cheese makes how many sandwiches? So you did all of those calculations internally. What I'm asking you to do is to stop doing it internally and write out your work. That's it. All of the chemical equations that we've ever worked with, that's all you're doing. You're writing out those conversion factors and those setups. You've done this in your head. Why did you say 4 sandwiches? It says how many could you make, right? Shouldn't the maximum amount of what you could make be the larger number? You have to go with the lower number. Why?
Because you don't have enough bread.
You ran out of bread. Right? So if we want to bring in now chemistry language to back this up, well, bread is a reactant. that reactant limits the amount of product that we could make. So we could call bread a limiting reactant. That's it. What would cheese be? It would be an excess. It would be the excess reagent or the excess reactant. That's it. Okay? What happens when we scale up to chemistry is now instead of looking at nice, easy things that we can physically grab a hold of and do that math in our head, we're looking at numbers that we can't deal with in our head. Why? Because they're massive. Okay? Or they're decimal values. We have to have this process to support those calculations. If we don't have the process behind it to support those calculations, what happens? The whole system crumbles and you can't solve. Follow the process. Make sense?
I
Okay.
just want to grilled cheese.
That's fine. So, 2 moles of sodium carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. How many moles of sodium hydrogen carbonate are produced? Why is this a more difficult question?
There's a lot more letters and numbers.
There's a lot more letters and numbers. Arguably, I would say all you did is instead of doing a grilled cheese sandwich, you now just further elaborated on what you needed for that grilled cheese sandwich. Okay? You needed 2 slices of bread, a slice of cheese. You also needed butter on the sandwich so that when you grill it, you get a nice char. Okay? 3 components. Okay? The numbers don't quite easily match up, and then you're seeing weird symbols, and you're trying to put those symbols and numbers in. Ultimately, what's happening is that this is now butter. This is cheese. Okay? And even in the case of the previous example, there's still a bunch of letters there, and yet you didn't try and go through and say, well, I have 1 H, so that means I can make 1 A. What the F are you talking about, H and A? Well, there's an H in cheese. There's an A in sandwich. Why'd you not see how those matched out? I mean, really, there's no H's in sandwich. That's a lie.
L.
Come on, there's a
There's no
word
L's,
there.
but there's no L's in
No,
there.
L
There's no
plus.
W's in cheese.
There's no W's in cheese. There we go. Okay? So we couldn't possibly make a sandwich because there's no W's in those components. You took those letters and you represented them as a physical object. The exact same thing is happening with chemistry. You need to take the letters and numbers of H2O and say that is a single thing. That single thing just happens to be represented by those symbols. Right? So how would we go through and solve this? Just like with the sandwich example, we had to look at each of the ingredients to translate into our product. What is our product in this case?
Sodium hydrogen carbonate.
Sodium hydrogen carbonate. If you don't like that symbology, you can use whatever symbology you want, as long as you then translate it to sodium hydrogen carbonate later. Okay? That would be the substance. What is the measurement? Moles of sodium hydrogen carbonate. What ingredient are you using to make that?
Water, CO2.
Okay? We're using 3 different ingredients, but just like with our sandwiches, we didn't jam all the bread and sandwiches and cheese into one big thing. We did them individually out, right? Okay, so we need to do the exact same thing here. You need to do it individually out. I want to convert the moles, whoops, did not mean to switch colors, the moles of the sodium carbonate. I had 2 of them, right? I want to convert those into moles of the sodium hydrogen carbonate. How much of each of those do I need? What is that conversion factor?
It's 1 to 1.
How do we know it's 1-to-1? Where did you find the amount of bread that you needed for a sandwich?
In the question.
Sort of. In the equation. So go back and look at the equation. Sodium hydrogen carbonate. Where does sodium hydrogen carbonate show up in the equation? Sodium hydrogen carbonate. It's okay. At the end, and what's the number?
2.
2. What is that 2 referencing? that I will make 2 of these if I have all of the other pieces in the perfect ratio. What is the piece that I'm most concerned about right now? Na2CO3. How many Na2CO3s do I need?
2.
What does it say in the chemical equation?
2 moles.
Where does it say 2 moles?
Right there, where your finger just was.
Okay, so this is 2 pieces of information. You're saying, oh, it says 2, because right where my finger it says sodium hydrogen carbonate is 2 moles. Did you already use that?
Yes.
Yes. Does that 2 moles of sodium hydrogen carbonate relate to, sodium carbonate relate to sodium hydrogen carbonate? That just says 2 moles of sodium carbonate. Period. The end. Finito. Does that say anything about sodium hydrogen carbonate? No. This conversion factor we just said is found where? In the chemical equation, which means
It's in the
look in the chemical equation. Okay? Don't just say, well, I see sodium carbonate, so that must be it. No. Sodium carbonate shows up in a lot of different places. Okay? You have to find where it's relevant to your solve. The relevant to your solve is because it's being tied to sodium hydrogen carbonate. That isn't happening in this 2 moles of sodium carbonate. That does not show the relationship. That just says I have it. That's it.
So it should
Okay?
be 1.
It should be 1 because when I look at sodium carbonate being tied to sodium hydrogen carbonate in the chemical equation, what is the number associated with the sodium carbonate?
1.
1.
So does that mean that they're all 1 then? There's no number in front of them associated?
They're all 1.
Okay.
He said we're not all, because it is a 2.
Okay? So that's where we have to be careful. As you start, well, they're always 1. No. Read the equation. Use the information you're given. How do you determine what those numbers should be?
You have to balance the equation.
You have to balance the equation. Are you responsible for balancing equations? Yes, that was Unit 2. This is why it builds. This is why in Unit 2 I said you have to do this. If you don't do it, Unit 3 still crumbles. Okay? Which means the answer I get is 2 divided by 1. 2 times 2 divided by 1 would be 4 moles. So the most I could make would be 4 moles of sodium hydrogen carbonate. The most sandwiches I could make in the previous case was 5. Was that the answer?
No.
No, it wasn't. Why was it not 5 sandwiches in the previous example?
Because
You didn't have enough bread.
I didn't have enough bread. How did I get 5 sandwiches?
you had 5 cheese.
I only looked at the cheeses. Have I looked at all of my reactants?
No.
So what do I need to do?
Go through your reactant.
I need to go through the other reactants. Do that now. So we're going to put this little bit of tidbit in the recording. I was able to write down the information that's up there in purple and blue and walk around the classroom twice. And you're like, well, that's not that big a deal. I saw a lot of people that barely had written the stuff that I have up here. Okay? What I see that is a commitment to not write. Okay? You were told exactly what you needed to do. You needed to start doing it immediately. I get students all the time saying, I can't write. I don't have time on the exam to show all my work. You don't have time on the exam to show all your work because you aren't committing to showing your work. Every time you look at a question, you're like, I don't think I need to write anything, so I'm going to try and do this in my head. Oh, there we go. There's my answer. I bubble it in. You got it wrong. Why'd you not get it right? Because you didn't show your work. Well, but it took too long to show my work. No, it took too long because you looked at the question and said, I think I can do it in my head, instead of just saying, I'm going to start writing right away. Right. It's a writing class. Write. Right? I cannot stress it enough. The instant you see a question, you need to start underlining important things. Write that information down. Okay? It says moles. That means amount. Okay? Put that information down. Commit from the instant you start a question that you are going to write something down. That commitment out of the gate will allow you to write information down. It will also allow you to get the answer right. Okay? Or at least to be able to see that what you're doing is wrong. Okay? For those people that are like, I can do it in my head though, that's cool. Eventually you won't be able to. Okay? And when that happens, you'll start getting everything wrong and you'll be like, God, that teacher sucked. No, you didn't commit to writing things from the get-go, and you're making simple math mistakes in your head. Okay? Maybe you're not stressed right now in this point in the semester. Some people are. Okay? If you're not stressed, you're able to think faster and cleaner and clearer. Okay? The instant that stress builds, you've lost that mental capability. You also now don't have the skill set to write the information down so that you don't have to think about it. Writing it down, even when it seems silly, builds the muscle memory to allow you to do things faster so that when you do need to do it, you're already set to write it down faster. Okay? Commit from the gate to write, period. So, if we go through and look at this, second one, I don't want moles of water shows up in the denominator. What do I want?
You want NaHCO3.
What is the numbers? What is that ratio found? From the chemical equation. So I go back to the chemical equation. There's a 2 in front of the sodium hydrogen carbonate. There's a 1 in front of the water. The answer comes out to be 4. What can I do with the next one? Same process. Moles of CO2, moles of sodium hydrogen carbonate, 2 over 1, the answer comes out to be 2. My answer is now 2 moles of sodium hydrogen carbonate is the most I can make. It's that smallest amount. CO2 is now my limiting reagent. Okay?
So with this, we're just looking for the limiting reagent throughout all of this. We're not looking for, I mean, unless we do have to balance it out, which I know we will have to. But this is basically just finding the limiting.
What were you asked to find here? Were you asked to find the limiting reagent?
No.
No, you were asked to find the amount of moles of sodium hydrogen carbonate produced. To find that, what must you also know?
What's the limiting reagent?
What's the limiting reagent? So that limiting reagent is built into the question, and it's not explicit. If you see a question that lists out amounts of a lot of the reactants or all of the reactants, it's a limiting reagent question. Why are we giving you all of that information?
So you can find the limiting reagent.
So that you can find it. Okay? Could the question have been written differently?
Yes.
Yes, I could have said, what's the limiting reagent? Do you still have to do the same work?
Yeah.
Yeah. Okay? And there's other ways that you can set it up to solve. Ultimately, what we're doing is we're taking all of the numbers that we were given with different units, and what did we do to all of those numbers? What did we do with the numbers? I took 2 moles of sodium hydrogen carbonate, or sodium carbonate, and turned it into 4 moles sodium hydrogen carbonate. I took 2 moles of water and I turned it into moles of sodium hydrogen carbonate. 1 mole of CO2 and I turned it into 2 moles of sodium hydrogen carbonate. What did I do in that whole process? I converted the numbers into a unit that was the same. Why would I convert them into a unit that's the same? Sort of. So that I can make a comparison. I can't compare different units. They all must be the same for me to make a fair comparison. So the whole point of this process is just to get all those numbers into a unit that is now comparable. Whatever that unit is kind of arbitrary. Okay? A lot of that is going to depend on what the question is asking. Okay? If it's just asking for the limiting reagent, I don't need to get them into products. I could make comparisons between the reagents. I could convert 2 moles of sodium carbonate into moles of water. Now I can compare that result to the water. Okay? It all depends on the question being asked. My argument with most limiting reactant questions, it is easiest just to go straight into the final product. Why? What do most limiting reactant questions ask about? The final product. So just take it to the product because you know you're going to end up there anyway. So just push to that extreme. Okay? Are there other steps that you could have taken? Yes, ultimately they're going to be the same number of steps. Okay? You really aren't changing the amount of calculations, at least not by a lot. At best, you lose 1 calculation step. You might say, well, that's time saving. Yes, it is time saving if you've already committed to write stuff down. Okay? And in that case, the time saving you've saved, 15 seconds. Okay? Almost everybody's turning in the exam early. 15 seconds isn't going to save you. Okay? So spend the time to just write it all the way out. You can do an analysis later.
Couldn't you technically have skipped the H2O part of, and just, because it's basically the same as the sodium carbonate? Well, no, you have to write it out because you changed the number, but still.
So what you're trying to do is say, well, with this question, could I have ignored these things? With this question, you could ignore a lot of things. Is this question going to show up on your exam?
Probably not.
So don't try and build shortcuts to one question, because shortcuts to one question will only work for one question. So stop trying to circumvent the amount of work that you have to go through and do. This again goes back to commit out of the gate. You need to write it down and just do it. Okay? There's not a lot of things I'm telling you to do on blind faith. This is one of them. Blind faith, write it down. Okay? When it is written down, you can now have that evaluation. Don't know what to write down? 3/4 of the information up there was written in the question. You're literally just copying the question. Okay? You're just deleting words.
But it should be
I don't need if.
Even as you're copying the question, your brain is figuring out how to process that information. That's one of the things. It may seem like extra time, but it allows your brain to focus on the individual pieces of information and begin figuring out how to put them together so that they make sense. Cognition.
So if we just delete stuff from there, delete the English language. Sorry, Greg. In that deletion process, do you see something that might stand out of like, oh, I need to solve for that?
The blank and mold sodium hydrogen.
Why are you saying that? Why are you saying that that's the one I'm solving for?
Because there's no number.
There's no number there. I now know that that's the one I need to solve for. The English language can sometimes be confusing, so you can start to delete things from it. Sometimes it directs you to an answer, sometimes it doesn't. Right? So if you can start to process and pull that information out, that can be helpful. Okay?
What I'm hearing is bring white out to the test.
Do this one. 1.5 moles of hydrogen. We'll come back to it. Because nobody made an observation about the last one as a potential shortcut. So since you aren't making that shortcut, we don't need the counterexample. Percent yields. The whole point of a percent yield is to standardize your result. You all did the copper lab, right?
Yep.
Right? In that copper lab, when I went through and did it, I found that I had 5 grams of copper in my sample. Okay? Who had more copper, you or me?
I don't know which one you did. Because I know them, whatever it's called, the one that starts with M, had like 70.
Irrelevant. I found some random sample. Had 5 grams of copper in it. Should we mine malachite, azurite, or my sample? There's an adventurous one. Yes, mine, because he had 5 grams, everybody else. Did anybody get anywhere close to 5 grams of copper in your samples? No, so we should mine mine. That 5 grams of copper that I got came out of 200 tons of dirt. Does that change your answer? Yeah. The raw numbers are meaningless if you don't know where they came from. That's the point of a percent yield. The percent yield allows us to make a comparison to say, well, that 5 grams out of, 200 tons comes in to be like a, 0.1%? I don't know what it is, but let's just say it's 0.1%. And you all got like anywhere from, it looked like 2% up to 50%. Okay? All of your dirt samples had more copper than I did. Okay? The percent yield allows us to see that. Okay? So a percent yield or a percent recovery. takes what we actually obtained, which comes from an experiment. How many of you are going to do an experiment in lecture? No. So how would we get the actual yield in lecture?
The information will be given.
It has to be given to you. Okay? How could we say it? Say, well, the actual yield was this. That's a bit too explicit. How else could I say it? The actual yield of what? Of reactants? Would I run an experiment to obtain reactants? No. What would I run an experiment to obtain?
A solution of product.
Products. So I could say yielded 43 grams of product. 43 grams of product was produced. All of those are actual yield descriptions. Okay? You just have to recognize that that's what that number means. You have to interpret the English language to get you the actual yield. Okay? The theoretical yield is oftentimes referred to as a calculated yield. Okay? Because what the theoretical yield is the maximum amount you could possibly make. Okay? That would come from knowing what?
Your sample size?
That would come from knowing,
From the equation.
I can sort of accept the equation, from knowing the giant freaking letters at the top of the slide, the limiting reactant. So to do a proper percent yield calculation, what do you also have to do? A limiting reactant calculation. Right? So it stacks very quickly and heavily. Admittedly, we have decided for Chem 130 that that is too much work. So instead what we go through and do for a percent yield is we tell you we actually obtained this amount from 4.3 grams of starting material, and it was expected to produce 16 grams of product. So we get three numbers. One is the actual, one is the theoretical, and one is... What's that? The other number given is just a random number to mess with your head. Because if we only give you two numbers, there's only two possible multiple choice. Actual over theoretical or theoretical over actual. So we have to throw in another number. So when you read a percent yield question, what you have to go through and do is delete the one that isn't useful. Okay? Well, what's the one that's not useful? When we look at an actual and theoretical yield, what are the units that come out for the percent yield? If the actual is the amount of product, what should the theoretical be?
Just guess of the product.
The amount of product. It should be a calculated amount for the amount of product, which means the actual yield is grams of product. The theoretical yield is grams of product. What are the units on percent yield?
Percent? Yeah, percent.
Just percent. Your grams of product cancel. This means the units for actual and theoretical yield need to be the same. Why? So that we can make a fair comparison between them to calculate a percent yield. Okay? So when we go through and do this, you just need to find the two numbers that are referencing the product. Once you've done that, it's now putting them together into the formula. Okay? Where it should be the actual over the theoretical. Okay? Make sense? Okay. So, we went through and did this top question. 2 moles of sodium hydrogen carbonate or sodium carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. How much sodium hydrogen carbonate could theoretically have been produced? 2. Where'd you come up with that number? It was literally the one we just did the math on. So we could go through and switch this question around and say 2 moles of sodium, or all of that information. 5 moles.
So then would it be 2 moles of sodium hydrocarbonate over the 0.5?
So we can incorporate that question in. The calculated yield was determined to be 2 moles of sodium hydrogen carbonate. Right? If we're being asked for a percent yield, the percent yield was for what?
The actual result over the theoretical result.
It said sodium hydrogen carbonate, right? So we would go through the question and find, where does sodium hydrogen carbonate show up? Well, there we go, right there. Where else does sodium hydrogen carbonate show up?
And then the amount of moles actually that we got.
The 0.5 moles of sodium hydrogen carbonate. What's the point of all those other numbers?
To confuse.
They're to confuse you and only to confuse you. So you can ignore those. Once you've identified what your percent yield is, you just need to find the numbers that are tied to those. So now the question becomes, should this be 2, whoops, where's my pen? 2 over 0.5 or 0.5 over 2?
0.5.
Why 0.5 over 2?
Because 0.5 is the actual amount of sodium hydrogen carbonate we got. Theoretically, we should have gotten.
From the question, it tells you the 0.5 was the produced, that's your actual. From the question, the calculated yield is your theoretical, that was the 2, which means it has to be 0.5 over 2, multiplied by 100, and we'd get our yield. Make sense? Does the yield have to be under 100%?
Yes.
Should the yield be under 100%? Yes. Does it have to be under 100%? No. The actual yield could have been misweighed. It could have been wet product. Right? If it was wet, you're now including the mass of water in that total, but now saying it's only that product. Right? So we could get a number larger than 100%. Right? Which means it's not just which of these numbers or which of these permutations gets me a number under 100%. It's make sure that you know the meaning of what those numbers are. Make sense? It must be actual over theoretical. Okay? So we don't have 5 minutes to review. You already kind of did this in Greg's class. Okay, so that's kind of nice. This is what I would argue is new content. Okay, dimensional analysis, I would actually kind of cross off this list because that's not new. Okay, we've been doing that for a while. You are responsible for knowing that a mole of objects is 6.022 times 10 to the 23rd objects. You're responsible for knowing that the periodic table tells you grams to moles. You're responsible for knowing what your balanced equations give you, what molarity gives you, your gas relationship, limiting reaction percent yield, and empirical formula. You are responsible for all of that new content. Okay? There was stuff at the beginning of the slides, or the beginning of this slideshow, that was supposed to be covered in the last unit, but because we were slow, we didn't cover it. Okay? That included topics like density, okay? Temperature, okay? Temperature versus heat, specific heat, energy transfers. Okay? All of that material is continuing into this exam. Okay? So it all makes an appearance. Okay? Most of the stuff that is up there is things that you need to be able to recognize that it's given to you. Okay? For instance, balanced chemical equations, that conversion factor, you're not told explicitly what that is. You have to pull the information out of the equation. Okay? Some of those are explicit things that you need to memorize. Some of them you just have to know where they're found so that you can use them. How do you use them? That's the dimensional analysis. What do we want? What do we have? Okay? And you have to ask yourself for each and every single one of those conversions. It takes time and it takes practice to manipulate those. I can go back and put that up. You can also take a picture if you take it within the next 5 seconds. We're at 3. I got at least one camera, so I'll delay. Okay. Limiting reactant and percent yield. Okay. This question is far more advanced than anything you will see on the exam. That's not true. Okay. This is pretty much the epitome of what we've talked about. This covers the entire semester in one freaking question. You should be able to do all aspects of this. Okay? How many different aspects are there? To answer this question, I think all of these questions have to be answered first. Right? And a lot of this comes from how do you decide that you need to answer that information. Right? And in that case, I would argue that it's reverse order. Right? The first thing that you would discover is, well, I need to do a percent yield. How do I do a percent yield? That's actual over theoretical. To get the theoretical, I need to know which one's the limiting reactant. So to do the limiting reactant, I'd have to know the maximum yield of hydrochloric acid was the limiting reactant. The maximum yield if magnesium was the hydroxide was the limiting reactant. To do those conversions, I need the balanced chemical equation. Right? To get the balanced chemical equation, I would need to know what type of reaction. I would need to know the formulas for each of those compounds. All of these things stack. Okay? This is how the semester has been built, so that you can slowly master the material early on, so that when we get here, you aren't panicking about everything that we talked about already. You're now reviewing it as part of this process. You should be able to go through and solve this question, okay, in 30 seconds. I'm just kidding. This is probably more like 5 minutes, okay? But we're out of time, so we can't do that. If you have specific questions about the practice final or the practice exam, you can for sure ask me. I've got lots of office